right? I thought there'd be data. Is anyone out there?
Okay, let's get started. I just posted a new homework, and if you had trouble with the first one because of prereq and your background, I think you're going to not have trouble with this one because it's much more focused and it's not asking you things from outside of the course. So there aren't too many concepts on this homework. So if you know them, and you're going to get it done. Okay, so we were talking about doing transformations of distributions of random variables. Actually, before that, does anyone have any questions about anything? I want to start sharing my screen while I wait and see. Okay, so yeah, we're still in section 1.2, which is one-dimensional transformations. And last time we derived a formula. So if we have x continuous with some PDF, f sub x of x, and we have y, a random variable defined as a function of this random variable. And we basically have g nice, and you'll see that a few times on the homework. Like you can invert it, you can take the derivative, it is differentiable, nice and continuous, all of that. Then we showed that the PDF for y is the PDF for x with the inverse function plugged in times the absolute value of the derivative. We just haven't gotten to really use this yet, although you did on problem 7 on the homework, presumably, on the first homework. So my first example of this is an important distribution for us, and the specific example, while it's going to seem not a very interesting transformation, is going to be a really important transformation for us throughout this course. And so I wanted to, I think I already introduced the gamma distribution. So here is an example. I think I only introduced it kind of in a margin one day when I didn't actually plan to do it. But we say that x has the gamma distribution with parameters alpha and beta. So those are parameters and they both need to be non-negative. This means that the PDF is 1 over the gamma function, which I will define today, of alpha, beta to the alpha, x to the alpha minus 1, e to the minus beta x, and it lives on 0 to infinity. So I still need to define the gamma function, but it's just a constant. And before I do the transformation, the gamma distribution it comes up a lot for us, and it has 3 distinct shapes. So depending on the parameter alpha, so alpha is known as a shape parameter for this distribution. And my beta is known as an inverse scale parameter, but if you flip the betas like some people do, it's known as a scale parameter. But I just wanted to look at the shape parameter. So it does have to be greater than 0, but you'll note that if alpha is between 0 and 1, this exponent up here could get negative, giving us a 1 over x kind of thing, which is going to like shoot off to infinity as x approaches 0. And so here are the 3 main shapes you can get out of a gamma distribution. If alpha is greater than 1, you get a kind of, I don't know, skewed thing like this. The lump moves around depending on where alpha and beta are. If alpha equals 1, many of you have noticed already that this is an exponential distribution. And if alpha is 1 and you plug things in here, well, let me say something else about matching constants and not knowing the gamma function. So when alpha is 1, you get 1 over gamma of 1, beta to the 1, x to the 0, so that disappears, e to the minus beta x on 0 to infinity. And so this part looks like an exponential rate beta PDF. So we must have that gamma of 1 is 1. And I will define it today, and we'll see that that's true. But this is what I keep talking about not really having to worry too much about these constants. But anyway, you get an exponential, doesn't look that exponential, starting at beta and going down. And I wanted a box. These boxes are this isn't working out as neatly as I had planned. And then if alpha is between 0 and 1, you get kind of an asymptotic thing. It shoots off to infinity at 0. Okay, so the transformation that I wanted to do today is a very simple one, but it's going to be important. So here's the example. Let's suppose that x is gamma alpha beta. And suppose that a new random variable y is defined by a constant c times x, for c a positive constant. So let's find the distribution of y. We are often going to need to multiply gamma random variables by constants. That's why we're going to need this one again and again and again. So the function y equals g of x is c times x. And if you invert that, you want to solve for x. So x is g inverse y is y over c. And we're ready to go. So fy of y is fx of x, of g inverse y times the absolute value of the derivative g inverse y. And this would be a little easier if you had the gamma PDF in front of you, but I don't want to scroll back up to the other slide. So I'm just going through the gamma PDF, and in place of every x, I'm putting a y over c. I have 1 over gamma of alpha, beta to the alpha. It used to be x to the alpha minus 1. Now it's y over c to the alpha minus 1. Okay, so and then e to the minus beta x becomes e to the minus beta y over c. And the indicator from 0 to infinity, x becomes the indicator c times y. And then don't forget to multiply by the derivative of g inverse out here with respect to y. And that is the absolute value you get of 1 over c. Clearly, we don't need the absolute value because c is positive, but since it's one of our first examples, I'll leave it there. And so this indicator can be simplified. Since c is positive, if I divide through by c, nothing is going to flip, right? So this implies that y is between 0 and infinity, which is what I'd rather report than where cy is. And so I'm going to simplify it just a little bit down to, looks like we have beta over c to a single alpha. That's combining this 1 over c and these 1 over c's. And y to the alpha minus 1, e to the minus beta over c y, indicator 0 to infinity of y. So the important result that we're going to keep needing is if you multiply a gamma random variable by a positive constant, then you get another gamma, and specifically that constant ends up under the second parameter. So the conclusion here is that y has a gamma distribution with parameters alpha and beta over c. We're going to need that for real statistics like hypothesis testing and confidence intervals. And c has to be greater than 0. If not, you can still do this problem, but you wouldn't call it a gamma, but you would kind of understand that it's like a gamma flipped over the axis with negatives, but it's not technically a gamma distribution with a negative c. Is everybody okay with that? So I am going to refer to this later. I'm going to say, remember when we multiplied a gamma by a constant and it ended up under the second parameter in the gamma distribution? And hopefully you'll think, yes, I remember. Okay, so if there's no questions, let's talk just a little bit about the gamma function and its properties. The gamma function is denoted by a gamma, and it has some argument, typically an alpha, and it is defined to be the integral from 0 to infinity of x to the alpha minus 1 e to the minus x dx. And alpha here has to be greater than 0. You saw it appear in that PDF. I said it before, but I want to emphasize again that if you see 2 letters next to or like in a gamma thing, that refers to a distribution. And if you see 1 letter or symbol, that refers to the gamma function. Basically, this is the constant that makes our PDF integrate to 1. So let's check out part of our gamma distribution. If we look at the beta to the alpha, x to the alpha minus 1, e to the minus beta x without the gamma part, and we integrate from 0 to infinity dx, then we can make the substitution. We can let u be beta times x, and then du is beta dx. And so we can take one of these betas and put it over with the dx. And we'll end up with the integral. Now, if beta is positive and x went from 0 to infinity, u is going to go from 0 to infinity. So the limits of integration stay the same. Alpha minus 1 of these betas get squished in with the x, and we end up with u to the alpha minus 1 e to the minus u du. And so that is the definition of the gamma function. It's just an integral done with a different dummy variable. But this function is just the thing that makes this integrate to 1. Okay, and some properties. I guess I just want to talk about 3 for now. The first one is that gamma of 1 is 1. And that is, I'm not even going to write it. That is super easy to see if you go to the definition and you plug in 1 for alpha. And then you can either integrate the lone e to the minus x, or you can say that's an exponential with rate 1. And it's normalized. The coefficient 1 is in front, so it integrates to 1. Okay, next up, I'm going to have to restrict alpha to be greater than 1. Gamma of alpha can be written as alpha minus 1, gamma of alpha minus 1. Now in this property, I'm not requiring alpha to be an integer, but if it was an integer, this is going to lead us recursively to a factorial type thing, which is property 3. So to prove this, we would use integration by parts. And so gamma of alpha is the integral 0 to infinity x to the alpha minus 1 e to the minus x dx. And I can let this part, the x part, be u, and this part be dv, and then du is alpha minus 1 x to the alpha minus 2 dx, and v, the integral of dv, is negative e to the minus x, and let's go. So this integral is going to be the u times v, so negative x to the alpha minus 1 e to the minus x, and that's got to be evaluated from 0 to infinity, minus the integral of v du, and the minus and the minus over here is going to turn this into a plus, the integral 0 to infinity of, let me rewrite it. Let me put the alpha minus 1 outside, x to the alpha minus 2 e to the minus x dx. So as, I'm not going to take the time to do this, I think, but as e to the minus x, as x goes to infinity, is shooting down to 0. Now x, depending on the value of alpha, could be increasing, but it's just an application of L'Hopital's rule to show that the e wins. And so when you put in infinity, that term goes to 0. When you put in 0, it's also 0 because e to the 0 is 1, and the x is 0. So that whole term is 0, I claim, and that is a L'Hopital's rule kind of thing if you want to show that. And so we're done, because what I see here is alpha minus 1, and then I see the gamma function, but with the alpha minus 1 replaced with alpha minus 2. So it's the gamma function. The alpha minus 2 is alpha minus 1 minus 1. Any questions? I like splitting the board like this. I want to trick you into thinking this is an actual chalkboard. Okay, so for part 3, if n greater than 1 is an integer, then gamma of n is n minus 1 factorial. We can see this because it's just a special case of part 2, right? Gamma of n, we know from property 2 is n minus 1, gamma n minus 1, and then we know gamma n minus 1 can be reduced to n minus 2, gamma n minus 2, again by property 2. And we can keep going until we hit n minus 1, n minus 2, down to 1 gamma of 1. But we know gamma of 1 is 1. So we're done with that. So let's move on to the next section, which is 1.3, which is 2 in a circle in a box. And what that means is we're in this overarching 4 important tools for mathematical statistics. Important tool number 1 was to find the PDF of transformations of random variables for discrete and continuous cases, at least when things were nice. And we talked a little bit last time about if things are not nice exactly, you can probably do the kind of CDF derivation that we did of our formula up to a point and then do something different. So this is about, I'm going to write bivariate transformations, but it's really, this is easily generalizable to n variables to another n variables. So bivariate transformations. Suppose I have, this is the setup, I have x1 and x2 with some joint PDF. They don't have to be independent or identically distributed or anything special, but a joint PDF that I'm going to call fx1, x2 of x1 and x2. And then suppose I have kind of nice functions. So I define a new random variable y1 as g1 of x1 and x2, and a new random variable y2 as a second function, g2 of x1 and x2. Then I'm just going to write down the formula for the joint PDF for the y's, just because it kind of mimics what we did in one dimension. And there is a part of the appendix of the notes that goes into Jacobian transformations. That's when you're taking a double integral and trying to transform the space. So that's what's going on here. But the joint PDF for y1 and y2 is fy1, y2, y1, y2. Just like before, we're going to start with the PDF for the x, or in this case, the x's. Before we plugged in g inverse of y. Here I'm going to plug in, and I do have to define what I mean by these inverse functions. I'm going to plug in what I'm calling g1 inverse of y1 and y2. And then for the second argument, g2 inverse y1, y2. And I will define those because this system of equations, they have to be inverted simultaneously. So g1 inverse is not exactly an inverse for g1 alone. It means that you've solved for x1 in that system, and we'll get there. But also I have to multiply by the absolute value. Now before we had a derivative, and now we're going to have what is called a Jacobian, which is a matrix of derivatives. So where J is the Jacobian that I'm going to define as follows. So if you've already done this, you might have defined this slightly differently. And if you want to do that, that's okay. And if you did define it differently, then your formula, so I'm going all the way over to the right, your formula would have an inverse up here. So there's more than one way. There's 2 ways to define the Jacobian. But for this joint PDF to work, we need to do it in this way. So it's going to be a matrix of partial derivatives, the derivative of x1 with respect to y1 across the top, and then the derivative of x1 with respect to y2. And across the bottom, the derivative of x2 with respect to y1, the derivative of x2 with respect to y2. This kind of is mimicking our one-dimensional case. You know, you see us putting the inverse g into the x PDF and then having some kind of more generalized derivative. I think it's highly believable, but again, I didn't want to talk about Jacobian transformations for double integrals. It's in the appendix of the book if you want to read it. And the second thing to note is that This is easily generalizable to transforming from x1 through xn to a new sequence y1 through yn. I mean, clearly there can be n things here and n arguments here, and this would be an n by n matrix. So in terms of defining the G inverses, let me just go to an example and talk about that. Because again, G1 inverse is not the inverse for G1. Let me write it in the corner. So if you solve for x1, that is how you define G1 inverse, but it probably took you both equations to do that. You're solving a system. And x2, if you solve for x2 in here, that's going to be defined as G2 inverse y1, y2. So let's try an example, and in the interest of time, I'm going to get more than one. I'm going to get three things out of this example. So one is going to be that it's just an example of this. The other, let me write it down. So as an example, I'm going to take x1 and x2, have the distribution. So I'm going to write IID over this, which we briefly talked about. It stands for independent and identically distributed. They both are coming from the gamma distribution with parameters alpha and beta. Another way to say this is that x1 and x2 is a sample of size 2 from this gamma distribution. I mean, sorry, a random sample. Random sample means IID. Okay, so I want to find the distribution of a new random variable y that I'm going to define to be x1 over x1 plus x2. And the first thing you'll notice is this is not an example of the formula I just put up. That takes us from 2 random variables to 2 random variables. But if you want to go from 2 to 1, in some cases there are going to be easier ways to do this. But for this kind of ratio, I think this Jacobian method is what I call it, is going to be the easiest way. And so what you do is you define y1 to be the thing you care about, and you define y2 to be anything, but not really. Some things are much more convenient than others. Then you find the joint PDF for the y's, and then you marginalize out the one you don't care about. So find the joint PDF for y1 and y2, and then integrate out y2 to get the PDF for y1, which is what we care about here. So yeah, 2 to 2, but possibly 2 to 1 if you go through the 2 to 2 procedure. Okay, so let's talk about this, this anything over here. We're going to have to invert a system. We're going to have to take some derivatives. And maybe most importantly, we're going to have to be able to integrate out y2 at the end. And any of those steps could get really hard if you don't make a good choice here. So my advice, anytime you have a ratio, I would recommend taking the denominator to be the second thing. This is, I don't know, this is not a fact, but this is my advice. If y1 is a ratio, let y2 be the denominator. It just makes things fall out really nicely. So let's do it. All right, I'll do the half board in case you're still writing. Now it's gone. Okay, so we have our two y's, and you'll notice I go from capital things to lowercase things. The capital things are random variables, but right now I'm just doing the algebra of inverting, and that's, I don't care if they're random or not random. So you could do it with capital letters, but we've got y1 is the specific function x1 over x1 plus x2, and we made up our own y2, which is g2 inverse x1, x2, which I'm claiming it will be convenient to choose the denominator. And then if you, oh yeah, the first one should be an inverse. They should both be, what did I do? They're not the inverses yet. Sorry, that should not be an inverse. Thank you. Now I'm going to invert them. And I just want to solve for x1, and that will be how we define G1 inverse. Again, it's not an inverse of this function. It is the first component of inverting the system together. And so y1, y2, it's easy to see, I guess, maybe not, I don't know. Because y2 is this sum, then this denominator here is y2, so I can get x1 by multiplying this y1 times y2. And then for the other one, I'm going to define the G2 inverse. And this one's going to be a little uglier. I'm going to just say x2 is y2 minus x1, and I've already solved x1 in terms of the y's, so I get y2 minus y1, y2. Let's get the Jacobian before we even try to start this. The Jacobian, oh, and by the way, I hate to scroll up and down for you, but the Jacobian is a determinant, and it has two straight lines on the sides of the matrix. It's a determinant. And then there's two more straight lines on the side in the formula for the joint PDF, and that's an absolute value. So they're meaning different things. Okay, so this is supposed to be the determinant of dx1, dy1, dx1, dy2, dx blah, blah, blah. Some people use the opposite Jacobian where they've interchanged the x's and y's, but then you're going to get a function of x, which is okay, but then you have to plug the y's back in for that, and the determinant is going to be the inverse of my determinant. So I don't want you to even think about that, but I'm just saying if you've done something like this and I'm not doing it in quite the same way, there are other ways to do it. Okay, so the derivative of x1 with respect to y1 is y2. The derivative of x1 with respect to y2 is y1. The derivative of x2 with respect to y1 is negative y2. The derivative of x2 with respect to y2 is 1 minus y1. So I'm going to take the determinant, which is going to be y2 times 1 minus y1 minus the product of the y1 and the negative y2. And we're going to get lots of cancellation down to just y2. So at this point, it is plug and chug. I think I'm going to have to do the half board. Otherwise, I just fly things up the screen that you're trying to write. So recall that, actually, before recalling the formula, we're going to have to plug stuff into the joint PDF for x1 and x2. So what is that? So let's write that down. The joint PDF for x1 and x2, because they're independent, that was one of the i's in IID. This is the PDF for x1 times the PDF for x2. And so this is 1 over, they were both gamma distributions. This is 1 over gamma of alpha, beta to the alpha, x1 to the alpha minus 1, e to the minus beta, x1, an indicator 0 to infinity, x1, times the same thing but with x2. And I'm going to simplify this as much as I can before going forward. So I'm going to combine some things. I've got 1 over the gamma function of alpha squared. I have beta to the 2 alpha. I have both x1 times x2 raised to the alpha minus 1, and I have e to the minus beta x1 plus x2. And then I just have these two indicators hanging out over here. Now we are truly ready to plug and chug. The joint PDF for y1 and y2, let me remind you, is the joint PDF for x1 and x2 with G1 inverse of the y's plugged in and G2 inverse of the y's plugged in times the absolute value of the Jacobian. And I've got the fx1, x2 written right above, and the, sorry, I have to scroll, x1 is y1 times y2, and x2 is y2 minus y1, y2. So I'm going to plug those in, and I get 1 over the gamma function of alpha squared beta to the 2 alpha. X1 was y1, y2, and then x2 was y2 minus y1, y2. So I think I'm going to pull out the y2 here and write this as y2, 1 minus y1. And that all gets raised to the alpha minus 1. And then we get e to the minus beta. And then I get to add these guys. So y1, y2 plus y2 minus y1, y2. And then I'm going to plug them into the indicators as well. We certainly get a lot of simplification in this exponent. Oh, and I forgot the Jacobian. Don't forget that. I just wrote down this part, and I need the Jacobian. So I'm going to multiply by the absolute value of y2. So I'm simplifying here is that this is 1 over the gamma function of alpha squared. And then in here, I've got y2 squared. And I've got I'm just trying to decide if I want to simplify more at this point. You probably wouldn't do this, but I have an eye on what we're going towards. So this is y2 squared to the alpha minus 1. And when you raise something to the exponent, to another exponent, you get to multiply them. So part of that is y2 to the 2 alpha minus 2. And then the rest of it is y1, 1 minus y1 to the alpha minus 1. I didn't have to separate those, but we are going, so I said I was looking forward. We are going to integrate one of them out. So separating them is nice, if you can. Okay, and then the e, I have e to the minus beta y2. And then I'm going to blow through this super quick because this product of indicators was the example we did last week or maybe Monday on twisted indicators, but they were called X and Y. And we sketched out the intersection of the region and it was nice and rectangular. So we got that the X, which is in this case Y1, is between 0 and 1. And we got that the Y, in this case Y2, is between 0 and infinity. And I know I still am missing that Jacobian, which I have to add on. But I just wanted to say from this indicator, because now I know that Y2 is positive, I can drop the absolute value. And then I can, right, so this is going to allow me to drop this up here. I wasn't quite sure if it was positive. And then I get to put it right in here. And so I get to add another y2. So I get y2 to the 2 alpha minus 1. Any questions? There's a beta to the 2 alpha. This is the joint PDF for y1 and y2, and I only cared about the distribution for y1. So at this point, you're supposed to integrate out y2. However, they look independent to me. So instead of integrating out y2, if you just pull out the y1 stuff and figure out what constant needs to be there to make this work, then we're done. But if that bothers you, let me show you why we can do this. The marginal for y1 is going to be, I'm going to integrate the joint PDF with respect to y2. In general, minus infinity to infinity, but in the specific problem, the indicator is going to cut us off from 0 to infinity. So if I write this out, I'm going to pull out all the constants, including the y1 stuff, the gamma stuff, the beta stuff, the y1 times 1 minus y1 to the alpha minus 1, and even the indicator that just involves y1. And then I'm left with an integral, so this is all supposed to be on one line. The integral from 0 to infinity, so that's going to take care of this last indicator. I no longer have to write it, it's 1 on that interval. y2 to the 2 alpha minus 1 e to the minus beta y2 dy2. This integral you can integrate without integrating. It looks like a gamma distribution. And we could put in the right constants and put them in front of the integral and get it done. But the quicker thing for this problem is to note that this is just another constant. And these are constants. And so the y part, the kind of important part of the marginal, we have that the PDF for y1 is like some constant times y1, 1 minus y1 to the alpha minus 1 times this indicator for some c. And I'll tell you exactly what the c is. Okay, so let's recognize and name this distribution and figure out the constant. If you go to your table, and I don't know if you have it now, but I would recommend having it when you're in this class, like so you can actually look right now as I say these things, if you can. So you go to the continuous side, and there's only two distributions that are on these finite intervals. One is the uniform distribution, which is a very boring flat line, which this is not, and the other is the beta distribution. So the beta distribution, I don't know if we talked about this yet. So A has, I think we did briefly. X has a beta distribution with parameters alpha and beta, means that the PDF for X is 1 over this thing called the beta function, which I'm about to define, but it's just a constant, x to the a minus 1, 1 minus x to the b minus 1, and it lives on 0 to 1. So from that, it appears that our y1, so this is just sort of a parenthetical side note, it appears that our y1 has a beta distribution with parameter alpha and alpha, right? If you put this exponent down onto each of these guys, then you can see a y1 to, oh, alpha plus 1, no, alpha. Yeah, alpha. But you can see that the alpha is taking the role of the A and B in the beta distribution. And so I need to tell you what this beta function is, which is sitting right here, but it's another constant. And, you know, you can name the distribution without knowing it. The beta distribution is my current favorite distribution because of the flexibility it has in modeling things between 0 and 1, which we have to do a lot in statistics, like for proportions and probabilities. When we estimate them, we might model that we have to model them somehow so that they're between 0 and 1. The beta distribution, so this is, the example is done. Squiggly line is usually my kind of thought break. If we're looking at the beta distribution with parameters A and B, the A and B have to be positive. That's the parameter space for this distribution. If you make them both 1, then all the x's disappear. So if A equals B equals 1, we get this distribution as 1 over this beta function of 1, 1, and then the indicator 0 to 1 of x. That is a constant. And we know exactly what it has to be because this PDF is a flat line over 0 to 1, and the total area has to be 1, which forces the height to be 1. My scale is off. It should look more like a square. This guy must be 1. And what we've seen here is that this particular specific beta distribution is the same as the uniform distribution on the interval from 0 to 1. So fxx is the indicator from 0 to 1 of x, and this implies that x has a uniform distribution on the interval from 0 to 1. We're going to write x squiggly line uniform 0, 1. In your table, you see other possibilities. So you can have a uniform from some A to some B. I think I parameterized it in terms of an alpha to an alpha plus beta. This is going to be a flat line distribution. And if the total area there has to be 1, since the length of the bottom is beta, this is going to be height 1 over beta. So I'm running out of time, but I just wanted to say quickly that other beta shapes that you can get, depending on how you choose your alpha and beta, you can get a nice little symmetric distribution on 0 to 1. You can get it sort of skewed to the right, like between 0 and 1. You can get it the other way. So it's a really nice flexible distribution. And you can even get a really like dramatic U shape. So that corresponds, this last picture corresponds to A and B being less than 1, because then you have x to a negative power. So 1 over x to a power, which is blowing up as you get close to 0. And the 1 minus x is blowing up as you get close to 1. So those are asymptotically going up. Okay. So next time, all I have to do to finish this section is define the beta function. It is defined just like the gamma function in that it's whatever makes this integrate to 1. And I'll show you a relationship between the gamma and beta function, which will further convince you that our previous example did give us a beta. And we are going into minimums and maximums. So what is that? Suppose I have a random sample x1, x2 out through xn. That means IID random variables from a distribution. So imagine going and grabbing that. You are sampling heights or something of people, and you just look at the minimum in that height. And then you throw that out and get a new sample of size n, and you look at the minimum there, and a new sample of size n, and look at the minimum there. That's changing depending on what sample you're drawing. So the minimum has its own distribution, which is not the same distribution as the original random variables. So we're going to talk about distributions of minimums and maximums. And we'll definitely get into moment generating functions. So next time we'll be in 1.4 and 1.5. And moment generating functions, super key to so many things. So don't miss it or miss it.